When you think about mathematics, I mean, would you agree with me that yes, there's a lot we do in mathematics, but maybe when it all boils down to it, we're trying to describe patterns of numbers. And a lot of times those patterns end up being described as some kind of equation. And of course, we can do things with equations. We can solve them. We can also graph them. But again, a lot of times our goal is to try to describe patterns as equations. I mean, think about it. If you have some kind of pattern that goes up and down, then you describe it with a sinusoidal equation, like a sine wave. If you have data that is constant, then you describe it with a linear equation. Okay, so we have different equations that can describe different kinds of patterns. But what happens if the pattern isn't like the same equation the whole time? Do we make up another kind of equation? Well, kind of. We actually make up a way to piece those equations together. And you guys know that this is headed towards a piecewise function. But I want you to understand that a piecewise function is still one function. It just happens to be made up of more than one equation. And you've heard of this definition before. I'm just kind of reminding you of it. I don't even know if you need to jot it down. You can if you want, but just look at it with me again. A piecewise function, it's still just one function, but it's made up of different equations. And often those equations are just a piece of that interval. And of course, that interval is always some type of x interval. And again, piecewise functions kind of give us a way out when the data isn't the same the whole time. Maybe the data is following some type of equation for some amount of x, and then suddenly the data follows some other equation for some type of x. And we can simply take those pieces, we put them together, and again, we get the infamous piecewise function. Now, if you want to, you can sketch my little diagram here. It's just a sketch. There are some values given, but I just want you to notice that I'm trying to model maybe kind of a really basic idea, maybe the profits of some type of company. We're trying to model something that has to do with money. And we're showing, or it's supposed to be showing, that the profits seem to be growing, and they seem to be growing in maybe some type of non-linear pattern by that yellow parabola. We'll say that this is a parabola. Again, even though it's just a sketch, we'll just go ahead and make that conclusion. So maybe the money is growing non-linearly, and of course you can see what that would look like. It's starting to grow and do pretty good. Now, for some reason, when x equals 4, and maybe that's the 4th year, maybe that's the 4th decade, whatever 4 represents, but for some reason when x equals 4, we have an anomaly. We have a value that is disjointed. We have a point. We'll actually talk later this year and next year in calculus that that's called a point discontinuity, basically because there's a hole in the graph. And then we have this disjointed value. So maybe for some reason the profits are now 20. Maybe that represents 20,000, 20 million, whatever. And then as time goes on, the increase in the profits appears to be linear. And again, we'll come up with an equation for that, but the profits are now changing a little more constantly. They've kind of calmed down a little bit. So we have a piecewise function. And again, this is just kind of made up. We could do one that's more heavy duty with a real application. But what if we want to write the piecewise function? What if we basically want to write the equations? Well, again, I know this isn't the first time you've seen this, but what we do is we say that there's a function. In other words, the whole graph put together, there's a function, but it's going to be defined in three different ways. It's going to be defined for some time as the parabola. It's going to be defined for some of the time as the parabola. Let me add a nice little closed circle here to the beginning of this interval. I should have had that there. So we have a parabola, again, the infamous x squared or y equals x squared, but we only have that parabola for some of the interval. Now notice or remember with me that an interval is always described as the x values. So to say that x is greater than 0 means that we're now to the right of 0. To say that x is greater than 0 means that we're only to the right of this parabola. But of course, it appears to stop at this spot when x is equal to 4. Technically, though, x cannot equal 4, so we'll just leave it as that less than only. Okay, now that describes, again, the piece of the graph that's the parabola. As I said, we have this anomaly. It's kind of like a point that's disconnected. Sometimes kids aren't sure how to describe that. Well, you describe it as the equation, and an equation is always a y value, so we describe it as 20. Now, it's a very simple equation because it's just a number. And it's only when x is equal to 4. So that's kind of a long way. That's a long way to describe a point. But it uses the right notation. 20 is the y value. Of course, 4 is the x value. Now, I find that it's these lines that, I don't know if they give kids the most trouble, but we sort of are the most forgetful. All that good stuff you learned about a line back in your algebra and pre-algebra days. Okay, first of all, a line is always of the form y equals mx plus b. Now, you would need some more detail to know that the slope of this line is 2. So let's just say that it's 2. Again, you would need some more detail to interpret that, but if we know that the slope is 2, we can write y equals 2x. But it's this y-intercept. Again, it's funny, the last thing in this problem that sometimes we are the most forgetful, where sometimes students will incorrectly grab 16 as maybe the y-intercept. But you know better than that. You know that a y-intercept is what it says. It's on the y-axis. Now, if the y-intercept is on the y-axis, then we kind of have to project backwards. Or we have to do a little bit of algebra math where you take your equation, as you've done before, and you solve it for your y-intercept by plugging in 16, by plugging in 4. What I'm trying to share is that you can still do this type of math, even though we're only talking about a piece of the line. So we get a y-intercept of 8 with the algebra, or by projecting backwards, and 2x plus 8 is our equation. Of course, we only want the piece of that equation when x is greater than 4. And again, we always use the x value. I'll say in a little more detail that we call that like a transition point of 416. And as you can see, the number 4 is used in all three of these domains. So what do we do with a piecewise function? Okay, and that's sometimes we're guilty as the math teacher or maybe the math curriculum that we don't do anything with it. We just kind of get the answers. You'll keep applying your math as you keep continuing in your science classes. That's often the goal. Learn it down here so you can apply it upstairs. But on a simple level, something we can do with our piecewise function is we can evaluate it. And I just want to make sure that you understand what it means to evaluate and really what it doesn't mean. So if you see the notation f of, I don't know, 3, you want to think back and you want to remember, okay, that just means plug in 3. Of course, when it comes to plugging 3 into this function, there's only one piece that it fits into. So when I plug in 3, it's only going to fit in the piece that calls for numbers like 3, numbers that are between 0 and 4. So I only plug it into the parabola. Of course, when I plug it in, it gets squared. I know it's pretty easy, but when I plug it in, it gets squared, so f of 3 equals 9. But it only equals 9. You don't plug it into the other pieces. They don't take the number 3. So in the third year, whatever x represents in the third year, my profits were 9 million, whatever it termed up. And of course, if I ask you to evaluate something like f of 6, well, you would plug in 6, but you'd only plug it into one of the pieces. And the only piece that accepts a number like 6 is the blue piece, because that takes numbers greater than 4. And 6 is a number greater than 4, so we can plug that in. And again, it's pretty easy math. It comes out to be 20, but it only comes out to be 20. Okay, and the mistake that I've seen is that students plug in everywhere, but you only plug into the piece that takes that number. Now, this is creating a piecewise function from a graph. Obviously, the other direction is to actually create the graph. And that's a pretty popular objective. In fact, that's where we want to finish this little lesson. We're going to make some graphs. This is what you guys did on the Nearpod. And it wasn't half bad. I mean, some of you nailed it. Some of you had a small mistake. But we're going over this because I want you to be good at graphing a piecewise function. I also want you to be good at making sketches. Not everything has to be kind of like a masterpiece. Sometimes you just need to get the main idea of the numbers, or as it says up here, the transition points or endpoints. Actually, I guess I didn't call them transition points. I just kind of call them starting and points and endpoints. But being able to label those kinds of things and also being able to describe the basic behavior of this function. Now, sometimes students will say, can I use a calculator, like a graphing calculator? I'm not going to take it away from you. Be careful, though. If you type this in the graphing calculator, it's going to graph the entire line 3 minus x. It's going to be like from negative infinity to infinity. And then it's going to graph the entire parabola. So it might be, what I'm suggesting here is it might be a little more confusing sometimes to use your calculator, or at least to try to rely on it too much. Okay, the approach that I'm taking here is more of a no calculator, think about the numbers approach. Of course, I want you to become that kind of student. How about this first piece, 3 minus x? Okay, if that kind of makes you get a little nervous, remember, it's just y equals. You can pretend it's y equals. You also want to notice that it's mx plus b. It's just backwards. M is -1. B is 3. And so even like in Algebra 1, the first thing I would do is I would start with the y-intercept. It gives me a place to start thinking about this line. Now, the slope is negative. So think about a negative slope. Now, I'm doing something here. I'm actually either just mentally or lightly sketching that line, because the mistake I see is that students will tilt the line the wrong way. And again, I know we're going back to the basics, but I think if most of us are honest with each other, we've all done it at some point. Just the line has a negative slope, so think of it that way. That dashed line is just to help me think of that line. Here's the crux of the problem. I want you to realize that -1 is a starting point or an end point. You can think of it either way. And that means that I should be investigating what happens if you plug in -1. I should be investigating what y value you get. Okay, now it's not hard math, but when you plug in -1, you get a value of 4. That's a y value. What this is saying is that when x is -1, y is 4. And that number, that point, is going to be the starting point or the end point of this piece. It is important. It needs to be labeled. It needs to be marked. It needs to be the place where I now draw my piece. Now, my piece has to be less than -1. Here's another kind of common mistake. I'm trying to get a lot of common mistakes in one problem. Kids look at this less than sign, and they think automatically about the graph going down. Like they think about this side over here, because it's kind of like going down. But that less than sign means left. So I really want your brain to say left of -1. Don't take the temptation and draw your graph to the wrong side. So again, we go to the left. All right, and maybe that took longer than it normally should or would to get that graph correct, but okay, let us continue with the other piece, x squared plus 1. Now again, maybe you're like, I want to put that in a calculator. Well, let's think about what you've learned. That's a parabola, and it's shifted up 1. I'm sure there's a week, a month where you spent a lot of time talking about stuff like that. A parabola that shifted up 1 would have a vertex at y equals 1. And it's a parabola. Now, since it's a parabola, it's going to have this basic shape. Notice that I've made it just like a dashed line, because I don't want to get too quick drawing it. I don't want to assume something. What would I be assuming? I don't know. Maybe I'd be assuming that these two pieces connect. And again, we get to the crux of the problem. You plug in your endpoint. If you plug it in, you discover truly where this parabola starts. Now, students will say, but it's not equal to -1. Am I allowed to do that? Yes, you're allowed to plug in -1, even though it's not equal to it. Because what I'm doing here is I'm finding what y value is going to match with this x value. And we discover that it's a y value of 2. But it's going to be one of those y values that is represented with an open circle. Now that open circle begins my parabola, my dashed line, which can now be sort of finalized. Okay, and this is an example of a piecewise function that has a jump. You'll learn in calculus next year that that's a jump. Actually, we'll talk about that this year. It's a jump because if you were traveling along this piecewise function, you would literally have to jump your y values to continue on your way. Okay, and that's okay. It's okay that the graphs don't connect, that the pieces don't connect. Okay, what I have shown here is a satisfactory sketch. You don't need it to be perfect, but you do need to have the values labeled. Again, the endpoints, starting points are labeled. Thoughts? Let's do one more. I realize that there's kind of a mix of information here. For some of you, you're saying, great, give me the assignment. But I'm trying to at least find something to make sure that we're careful about, that we can brush up on, and be able to nail these piecewise functions for now and evermore. So I've got 2x plus 3. X is less than 0. We've got 3. It's just like the number 3 for x's between 0 and 2. And then we've got the square root of x minus 2 for x's greater than or equal to 2. I'm just pausing a little longer because if you want to consider how you might start something, have at it. If you prefer just to listen again. This first equation is linear. What I like to do is give myself kind of a visual of what this line looks like. It starts at 3, at least it has a y-intercept of 3. It has a slope of 2. As I said in the other problems, sometimes the only mistake we make is just the tilt of the line. Now, x is less than 0 have already been basically determined that the y value is 3. So we have a point. It's an important point. It's the point x equals 0, y equals 3. So it needs to be marked on your graph. And then to the left is less. To the left is less. Now, technically, I guess I have a small mistake here, which can always be fixed up, but I filled in that circle. I was a little anxious to do that. It doesn't look like that circle is going to get filled in because I'm never equal to x. I'm never equal to 0. So we should take care of those items and let that be an open circle as you're not equal to 0. Now 3 is an equation, but this time it's an equation that lasts from 0 to 2. So if it lasts from 0 to 2, then it's going to be a line, a horizontal line. I think we can just draw that right away. Okay, and then we arrive at this last piece, which again, if you had to, you could type that in a calculator. If you're kind of like, I don't remember that. It is just a square root curve that shifted to the right. Remember, whenever you subtract from x, it's a shift to the right, which conveniently is my x value that I left off on. Now, if you plug in 2, pretty easy math, if you plug that in, you get a y value of 0. That actually just confirms that this shift point ends up being my starting point. So it's a square root graph. Square root graphs look like that. Again, if maybe you don't remember from previously. And the sketch I'm drawing is sufficient. Now I've got one last thing to kind of sort of finish here. I can't just have this line just stop since they don't connect. And since it's not equal to 2, then I have to clean this up and make that an open circle. Okay, so we have a piecewise function that's linear, and then it's literally constant because it's constantly equal to 3, and then it jumps as it's equal to the square root curve. Okay, I know you've seen these, but I want you to bring them back to the front of your mind, kind of brush up on them a little bit, and that's what this assignment is for. It's supposed to say, hey, get this right. I want to see you get this right, and be able to be confident with piecewise functions. It does come out of the textbook. Maybe you want to plan accordingly. I don't know if you're going to take a picture of page 39 and page 25, or if your textbook is in a place that you'll be able to look at it.